Alright, let's do some long division. I look at the lead coefficient and the lead term here, and I figure out that this goes in 4x squared times. So I multiply 4x squared by the entire expression, x minus 5, and I have 4x cubed minus 20x squared. I'm going to subtract all of this, which means I'll be adding in this column, and I end up with negative 4x squared plus 28x minus 39. How many times does x go into negative 4x squared? That is negative 4 times. And we'll put an x on there as well. So if I multiply that, I get negative 4x squared plus 20x. I'm going to subtract all of this, which means I'm adding, so the x squareds go away. And I'm down to 8x minus 39. How many times does x minus 5 go into this? 8 times. And if I multiply that, I get 8x minus 40. Let's subtract this whole thing. My remainder is 1. So this is my answer. And if I wanted to write my remainder, remember that it's 1 over x minus 5. To set this up using synthetic division, I use the coefficients from the cubed term, 1, negative 10, and there is no n term, so I put a 0 there, and then the constant is 2. To figure out what to divide by, I think about what makes this 0, and that would be a 10. So I look at my first column, and I add this straight down, and I get a 1. Then I multiply 1 by 10, and I get 10, and I add that column straight down, I get 0. 0 times 10 is 0, add it straight down, do it again, and here's my answer. So this is n squared, remainder 2. I can also write that as n squared plus 2 over n minus 10, because my denominator is always what I'm dividing by. Let's set this up for synthetic substitution. I'm going to put a 2, that's from the x to the 5th, a 1, and there is no x cubed, so I'll put a 0 as a placeholder. Negative 3 comes from x squared, 0 comes from x, and 3. And I'm going to plug in negative 2 over here. So I have 2, negative 4, 1 plus negative 4 is negative 3, times negative 2 is 6, negative 12, negative 15, 30, negative 60, negative 57. And this verifies that if you plug in negative 2, you get negative 57 as an answer. So let's set this one up. I have a 1, a negative 6, negative 4, and a 45. I'm going to put in, not x, but 5 over here, because that's what makes this 0. Carry down the 1, that's a 5, that's a negative 1, negative 5, negative 9, negative 45, 0. So this gives me x squared minus x minus 9. So I'm going to write it like this. X minus 5 is a factor times x squared minus x minus 9. And I can split this. Actually, nope, this one can't be factored, so it looks like we're going to have to use the quadratic formula again. So if we plug in our a, b, and c values, a here is 1, b here is negative 1, and c is negative 9. We get this. We can simplify this to 1 plus or minus the square root of 37 over 2. So one of our zeros is 5, and then our other zeros are this, given the quadratic formula. Why did we have to do it? Because this cannot be factored using the x method. In the next section, we are just combining like terms. So 4 plus a negative 2 is 2, and then negative 3i plus 8i is 5i. Think of I almost like an x and follow the usual rules. Here I have 2 plus 2, that's 4, and then 4i minus 4i goes away. I have to distribute the negatives for each of these. So this is like 8 plus 2 minus 2i plus 2 plus 2i. And then I consider all of the numbers together, that's 12, and the i's go away here, 2i minus 2i. To multiply these binomials, I'll use the box method or the area model. Negative 8, 4i, 20i, negative 10i squared. And that negative 10i squared I could write as a positive 10. So if I combine this, I get 2 plus 24i. To resolve the denominator, I can multiply by something called the complex conjugate. All that is instead of plus 2i, it's minus 2i. And I put it over itself, so we're not actually changing anything. This is just multiplying by another version of 1. Again, I will set up the box method, or the area model. And what's really nice about this, the reason we're doing this, is this diagonal cancels out, plus 2 minus 2. And the other thing that's really nice is I squared is replaced with negative 1, so this becomes 4. So the bottom of my fraction is just 5. Next up, I set up the multiplication for the numerators. 3 times negative 1 is negative 3, negative 2i, negative 6i, negative 4i squared. And I could replace this with a positive 4. So 4 minus 3 is 1, minus 8i. There's my answer. I could split it into 1/5 minus 8/5 I, but I think I'm going to leave it just like that. Here we set this part, a minus 3, equal to negative 7. If we add 3 to both sides, a is equal to negative 4. Next up, we put b minus 4i equal to 5i. So if we add 4 to both sides, we are going to, I guess we're just looking for a number to plug in because there's parentheses there. So what minus 4 is 5? The answer is 9. Similar here, 16, negative 2a. So 16 is equal to negative 2a, so a has to equal negative 8. And then I have 3bi is equal to 27i. So 3b is equal to 27, so b is equal to 9. So one thing that we like to do is we like to recognize that I to the 4th is just equal to 1. So we can figure out how many times that goes in there, and then simplify this. For example, we could say I to the 4th raised to the 6th. So power to a power, that's 24 times I to the 3rd. And this whole thing becomes 1 I cubed. And if you remember, there are only 4 values you need to know, and they repeat. I is equal to the square root of negative 1. I squared is negative 1. I cubed is negative I. And I to the 4th is 1. So this answer is going to be negative I. Here we distribute the negative, and we also mess around with these negatives inside of the square roots. We're going to make that equivalent to the second root here. So let's see if we can rewrite this. Negative 3 plus, and I'll make this the square root of negative 1 times the square root of 16 times the square root of 2. I'm splitting negative 32 into 3 different parts. After I distribute the negative, this becomes plus 4, and this becomes plus 4 root 2i. Notice the I is like a unit at the end, it's not underneath the radical. So I can take the square root of 16, that's just 4, and I can replace the square root of negative 1 with I. So this becomes negative 3 plus 4 root 2i, plus 4 root 2i. If I combine my 4 and my negative 3, I get this. And if I consider root 2i as a unit, I can add them. I have 4 plus 4 gives me 8. If I'm finding asymptotes, the first thing to note is the vertical asymptotes. The vertical asymptotes are the zeros of the denominator. So if I think about x squared minus 9 equals 0, there's 2 different answers here. Because this gives me x squared is equal to 9. If I take the square root, I have x is equal to plus or minus 3. So the first vertical asymptote is the vertical line x equals 3, and the other one is the vertical line x equals negative 3. The next thing to consider is horizontal asymptotes. And there's 3 different things to consider. We have to compare the degrees of the numerator to the denominator. The degree, remember, is the largest exponent in the expression. So here we have a degree of 2 and a degree of 2. So it turns out if the degree on the top is bigger or equal or less than the bottom, this top one should be, the top is less than the bottom. If it's less than, equal to, or greater than the bottom, different horizontal asymptote possibilities emerge. For example, if the top was smaller, our horizontal asymptote is the line y equals 0. If our top is the same, we take the 2 leading coefficients and we divide them. and that is our asymptote, our horizontal asymptote. If the top is bigger than the bottom, then there is none. In this case, they're equal. So if I look at the degrees, it's 2 over 2. And therefore I can have my horizontal asymptote defined as the leading coefficient divided by the leading coefficient. So that's y is equal to -3 for my horizontal asymptote. Since they state the domain restriction here is where this can't exist, which means the bottom can't be 0, and that's that x is not equal to 3 or -3. Let's use these same ideas for the next one. First of all, the vertical asymptotes are the zeros of the denominator. So if I think about this one and I put 12 and -7, I think -4 and -3 are the answer. This is how I could factor the bottom. So the vertical asymptotes are x equals 4 and x equals 3. Next up, let's consider the degree. The top and the bottom are equal. Therefore, we're looking at the leading coefficients, 1 over 1. So therefore, let me write that out. The degrees are 2 over 2. The leading coefficients are 1 over 1. So the horizontal asymptote is the line y equals 1. The domain restriction would be at the bottom. So the domain is that x can't be 3 or 4. We can't divide by 0. For the next section, we have these same ideas. First, we have vertical asymptotes, then horizontal asymptotes, but we add a number 3. Slant asymptotes only exist in very specific circumstances. First of all, the denominator has to have a degree that is greater than or equal to 1. Secondly, the degree of the top has to be exactly 1 bigger than the bottom. So let's go through these 3. For vertical asymptotes, that's the zeros of the denominator. What makes this 0? 3x minus 1 equals 0. Well, that's 3x equals 1. That's x equals 1/3. So for a vertical asymptote, we have x equals 1/3. For a horizontal asymptote, the degree of the top is bigger than the bottom, so there's none. For a slant asymptote, do the narrow band of specific requirements apply here? The degree of the bottom is 1, and the degree of the top is 1 bigger. What we do then is we start to use long division. So if I take 3x squared minus 9x plus 6 divided by 3x minus 1, it goes in x times. If I multiply that by the original, I get this. If I subtract it, that means I'm looking at negative 8x plus 6. How many times does this go in? And it's a fraction, which is kind of awkward, but we'll say 8/3. And if I was to multiply that, this would give me negative 8x. And it doesn't really matter what the other part is, because when I subtract this, it cancels out. And guess what the equation for my slant asymptote is? It's the line y is equal to x minus 8/3. So to find the slant asymptote, you use division, and whatever is there, you ignore the remainders. Y equals that expression. Let's look at another one. For the vertical asymptote, the zeros of the denominator, so that's x equals 9. For the horizontal asymptote, because the degree of the top is less than the degree of the bottom, it's going to be the line y equals 0. That's always the case. And for the slant, the bottom does have a degree greater than 1, but it's not true that the numerator's degree is exactly 1 bigger than the bottom. So we're going to say none for this one. So let's factor out a 2 here, and this gives us x squared minus 5x plus 4 is less than or equal to 0. And I can factor this into x minus 4 and x minus 1 is less than or equal to 0. These tell me my significant values. So I'll put a 1 here and a 4 here on a number line. And you could either plug in numbers or graph it. And you would be looking for when is the graph less than or equal to 0. And in this interval, it's not. In this interval, it is. And in this interval, it's not. We can write that expression as 1 is less than or equal to x is less than or equal to 4. Either method works. Graphing it or plugging in any number within those intervals. For this next one, my step one was to graph it and look for zeros. I found that 6 is a 0. I just did trace, and it was pretty easy to spot visually after plugging this graph into y equals. That means that x minus 6 is a factor. I used synthetic division. I set up 2, -12, 1, and -6 for my coefficients, and I divided this by 6 because that's the 0 for this one. So I guess I divided it by x minus 6. I found this, which means, using the special products, that if I was to factor this again, this would be a complex number. It would be root 2x minus I and root 2x plus I. And if I did the quadratic formula, I would find the same thing. The other zeros are imaginary, so the only real 0 here is 6. Now what does that mean for this graph? If I consider a line here at 6, I can test it. Everything to the left of 6, yes, it's below 0. Everything to the right of 0, no, it's not. So it's just x is less than 6. And I probably could have just assumed that once I saw the graph, if I didn't feel like testing all of the other possibilities. For this last one, I need to move the 1 over to the other side. So I have 2x plus 3 over x minus 1 minus, and this is x minus 1 over x minus 1 is greater than or equal to 0. If I combine like terms here, I have x plus 4 over x minus 1 is greater than or equal to 0. So the two significant terms here are going to be the -4 that gives you 0 on the top, and the positive 1 that gives you 0 on the bottom. If I look at a number line and I consider everything here between these different intervals, well, everything to the left of -4 is a yes, everything in this interval is a no, and everything to the right is a yes. So I could write this as x is less than or equal to -2, and x is greater than 1. It can't be equal to 1, so it has to be greater than 1. Oh, sorry, I wrote 2. That should have been -4.